Today we're going to talk about the definition of the derivative. The derivative is the instantaneous rate of change, aka the slope of the tangent line at a point. This is opposed to the slope of the secant line. If I take a curve and look at any 2 points on the curve and calculate the slope through those 2 points, that is the slope of the secant line. This is known as the average rate of change. And that's calculated simply using our slope formula. Right? So if this is x2, y2, and x1, y1, the average rate of change is just our slope m using our slope formula. We're going to take this slope formula as inspiration for how we calculate the instantaneous rate of change. If I draw a diagram and label this point x, the y value is going to be f of x, whatever our function is. I go a distance h to the right and put a new point, which is at the x-coordinate x plus h, and has a y-coordinate of f of x plus h. Again, whatever this function is, I plug in my x-coordinate, it's going to spit out a y value. The slope then is going to be what's called the difference quotient, which you may have learned in pre-calculus. Now, x plus h minus x is just going to be h. So, it's typically written this way. Now again, this is the average rate of change over this distance h. Where we get the instantaneous rate of change is we let h approach 0. As h gets closer and closer to 0, we end up with the slope right at that point, aka the instantaneous rate of change, aka the derivative. So we modify our difference quotient with a limit. In the limit, as h approaches 0, this will equal the slope of the tangent line, and this is our definition of the derivative, which we can represent this way. The triple equal sign indicates this is a definition. Now, this is not the only definition of the derivative, but we'll stick with this one for now. So before we learn our derivative rules, how can we use this to calculate the derivative of a function? Let's start with the function f of x equals x squared plus 2x. So it's going to look something like this. It's going to have an intercept at 0 and negative 2. It basically looks like this. So the slope's going to be very negative, and it's going to be 0 here, and it's very positive here. So the way that we would calculate our derivative is we would apply this formula. So the derivative as a function of x is going to be the limit as h approaches 0 of this thing. So I plug in x plus h to each of these. And be careful. You're going to want to write a minus sign and then probably a set of parentheses. One of the most common errors to make is to think that, you're done here. Oops, I screwed up here. That's supposed to be x plus h. So one of the most common errors is, one, you write this and you forget there's a second part, f of x. Next most common error is to fail to distribute that minus sign correctly. So I'm going to write minus, and then I'll use a bracket here, and then I just write my f of x squared plus 2x, all over h. And we have to keep writing our limit until we evaluate it. Now we multiply everything out on top. Distribute the negative sign. And so for polynomials, it should be the case that all of your non-h terms should cancel. Those cancel. Those cancel. And so I'm now left with at least one h on every surviving term, which allows me to factor it out and cancel it. Once that's canceled, you can now let h go to 0 by plugging in h equals 0, and you're left with your derivative as a function of x. And if you already know your derivative rules from Calc AB or perhaps an advanced pre-calculus class, you'll know that that is the correct derivative for this function. Now, it is annoying to calculate your derivative this way, but eventually you will learn the shortcut rules. So for now, hang in there. Do note that if you have a rational function or you have radicals, you have a slightly different way of solving these. So for instance, let's say your function were 2 over x plus 1, and you wanted to find the derivative of this. So if we apply the formula, in order to solve this, we're going to have a common denominator for the top. So that means we multiply the top and the bottom of this one by x plus 1, and then the top and the bottom of this one by x plus h plus 1. I'm going to go ahead and write the common denominator here. Do not distribute the denominator. That won't be necessary. I'm going to also, because I have a fraction divided by a single number, for convenience, just write that h down here. That is the same thing. If you have trouble with this one, write this as h over 1, and when you divide by a fraction, you multiply by the reciprocal. So when you divide something by h over 1, that is the same thing as dividing that something, or multiplying that something by its reciprocal. That's why the h ends up down here. Again, we're going to distribute this, and what will happen is all of the non-h terms will cancel. So the 2x cancels, the 2 cancels, leaving with just negative 2h on top. We can cancel that h. Now when we let h equal to 0, that's going to be an x plus 1, that's going to be an x plus 1. We are left with negative 2 over x plus 1 squared. And again, if you know your derivative shortcut rules, that is the derivative of f of x here. So I should have labeled this f prime of x, and this is f prime of x, indicating this is the first derivative. If your function is a radical, then what you're going to need to do is you will apply the limit, and the technique now is to multiply the top and the bottom by its conjugate, essentially. So you reverse the sign here. Which should be a familiar technique from limits involving radicals. You are taking advantage of the difference of squares formula by doing this, which will allow you to write basically this squared minus this squared. Again, do not distribute the denominator. The numerator, because that'll be this squared, that'll just be 2x plus h, quantity, plus 1, minus parentheses 2x plus 1. Again, don't be sloppy with distributing that negative. Now when we distribute everything out, again, everything that in the numerator that doesn't have an h should cancel out. Which it does. two x's cancel, the 1 cancels, leaving you with a 2h on top. We can cancel those h's. Once this h in the denominator is canceled, we can now let h go to 0. Notice each of these terms becomes the same down here. One of these plus one of these is 2 of them. And we end up with this as the derivative, which is correct. Now this is only the first form of the definition of the derivative. Again, going back, this formula gives us the definition of the derivative as a function of x. We have two additional ways of finding the derivative, but both of those are used to find the derivative at a particular point. If you want the derivative at a specific value, which I'll call c, one form uses almost the exact same formula, but instead of x, you have c. Now, what's going to be usually done with this, and I'll point out that this again comes from the idea of slope. If we replace x with c here, we end up with the slope right at c when we let this distance h approach 0. Now you could end up calculating the derivative at a specific value this way, or you could calculate the derivative as a function of x this way, and then just plug in a specific value of c once you get your derivative for a particular problem. That's not going to be the most common problem type. The more common problem type is you will be given a limit and be asked to evaluate that limit, but it in fact is the definition of the derivative. So for example, let's say I had the limit as h approaches 0 of 2 plus h cubed minus 8 over h. You could multiply this out and find the limit. However, what you're actually intended to do is to recognize, oh, this is the definition of the derivative for a particular function. How do I determine the value of c, and how do I determine the function? Well, you determine the function by looking at this part before the minus sign, because this is f of c plus h. The reason why you don't want to look at this part is it will not always be conveniently written as c and then whatever functions applied. It may be simplified as a number. If this number happens to be 0, it may be absent completely. So you are looking at this part. Treat this whatever plus h as a clue that that quantity it represents x. So in this case, your function is x cubed. And your c value is 2. So for later problems, when you are given this limit and you know your derivative shortcut rules, you are not asked to actually, or you're not expected to actually calculate this limit. You're instead supposed to decode it. Decode the function, decode the value at which you're supposed to apply it, find your derivative using a shortcut rule, and then evaluate it at that c value. Much shorter than multiplying this all out, canceling terms, canceling the h's, and evaluating the limit. The last form of the definition of the derivative looks a little bit different. Instead of the limit as h approaching 0, you're going to have a limit as x approaches c. Same concept here though. You have c, f of c here, x, f of x here. And so instead of having h approach 0, we're letting x approach c. So in other words, this point's getting closer and closer to here. Exact same thing. The slope of the secant line approaches the slope of the tangent line. And so this is just another way of calculating the definition of the derivative at a particular point. So let's say I had a similar problem to the one up here. Let's say I had limit as x approaches 3 of square root of as x approaches 9, of square root of x minus 3 over x minus 9. Again, we could calculate this limit using our conjugates strategy. So multiply by root x plus 3, top and bottom, only distribute the top, get cancellation of the x minus 9. However, increasingly, this is meant to be the definition of the derivative. The clue will be, you have a function of x here, so you're going to look at this thing, and then this will be your c. And as long as your x minus whatever the limit value is on the denominator, that's a good clue that this is the definition of derivative of this form. So here, our function is square root of x. Again, using our shortcut rules, this will end up being, the derivative will be 1 over 2 root x. Our c value is 9, and so when we evaluate this at 9, this will end up being 1/6. So again, increasingly you're not going to be evaluating your derivatives this way. You may be doing so initially. Instead, your goal is to identify certain limits as definitions of the derivatives, decode what the function is, if necessary decode the value at which you're supposed to evaluate it, use your derivative shortcut rules, and then calculate the limit that way.